இல்லை முன்னே. அதான் இங்கே ரூமில் அடைச்சிக்கலான்னு பார்த்தேன். எந்திரிச்சா சொல்லு. அப்புறம் அப்புறமாட்டி மாறிக்கணும். ஹலோ. இல்லை எந்திரிக்கல, தூங்குறேன். ஆமாம், நடுவில் பிடிச்சி தூங்கிட்டு இருக்கேன். எந்திரிக்கவே இல்லை. பிடிச்சேன் ஒரு 90 இல்லை ஒரு 20 வச்சுருக்கேன். இல்லை காய்ச்சல் இல்லை. ம் 6லேருந்து 8 கிளாஸ் இருக்குமா? அதுக்கு முடிஞ்சுன்னா அடிக்கிறேன், இல்லாட்டி அடிக்கிறேன் தான் மாமா பெரிய. சரி சரி சரி. ம் முடிச்சிட்டாங்க. என்ன ஹைட் கரெக்டாக முடிச்சிட்டேன். ஒரு இலைகால் 7:30 போல் கிளிக் பண்ணி முடிச்சிடுவேன். நீங்கள் சீக்கிரம் முடிச்சிடுங்க. லாஸ்ட் ஃபுல்லாக போட்டிருக்கவே நான் மாற்றிக்கிறேன். So we will start with today's session, week 4. This session involves first order system with ramp response, impulse response and frequency response, along with a start with the second order system with the step input. So we'll move on to some problems and questions regarding the said topics. So the first question is, which of the following is a second order system? So which of the following is a second order system? A, spring mass system for force measurement. B, temperature measurement by thermocouples, C. amplifiers, D. build up air pressure in bellows. So we have 4 examples and we need to find out which is the second order system. So in this case, the answer is option A, spring mass system by force measurement. If you see in second order system, we saw 3 components: one having a damping effect, and thermal sensitivity, and a time constant. And in the spring mass system, you have a mass attached to a spring, and the atmosphere it will act as a damping to the system, and it will provide some damping. And because of the spring, it has an inherent it will have a sensitivity which was discussed in the class. When if your the spring constant is more, it will affect the time constant as well as uh, your the sensitivity. So if you see B, we saw the previous weeks the temperature measurement, thermocouples. These are our first order systems. And then we have amplifiers and build up air pressures in bellows. So for this case, the answer is option A. The second one is next problem is a second order system would be critically damped. So second order system is critically damped when A. damping ratio is less than 1, B. damping ratio is equal to 1, C. damping ratio is greater than 1, D. damping ratio tends to infinity. So in the second order system, the case can be undamped, you have then underdamped, then critically damped, then damped, overdamped. So these 4 cases, it all depends upon the damping ratio. The damping ratio is defined as the C by Cc. Cc is the critical damping. So if you see, for the system to be in critically damped case, you need damping ratio to be equal to 1. So if you see omega damped, if you it's expressed as omega natural frequency of the system into root of 1 minus zeta square. Zeta is the damping ratio. So if you put zeta equals to 1, then this omega d will be then 0. There will be no damp. There will be no oscillations. It will have there will be no overshoot in the system. So that's the case. It's having critical damp. Overdamp will also have no overshoots, but the start will happen at a critical damp. And for underdamped, you will have a small overshoots close to the critical damp. At very low damping ratios, you will have a larger, higher damping, higher overshoots. And the oscillation can be even large when it will keep on the time to reach the steady state, or the error less than 5%, or so error which you require. That time can take longer, we having less damped or undamped system. So the answer is damping ratio equal to 1. Moving to the next case, the time taken by an underdamped second order system to reach peak output in response to step input is known as. So the time taken by an underdamped second order system to reach peak output in response to step input is known as A. settling time, B. response time, C. rise time, D. oscillation.
Is rice time.
Yeah, correct. It's rise time. So moving on, next question. A damping ratio of 0.7 is desirable for the measuring instrument because So damping ratio is C by critical damping files. So that's equals to zero point 0.7. It's required for measuring instrument for which cases. So A, it gives minimum possible settling time. B, it gives the instrument the highest sensitivity. C, no response occurs at this value. D, no overshoot occurs when the step input signal is applied.
It looks overshoot it will be little, but minimum settling time also it is also minimum settling time. I think it gives the minimum percent.
Yeah, correct. It's minimum A settling time. Overshoot will be less, and you desirable you go with zero point 0.6 to zero point 0.8. So this
Yeah,
is I mean zero point 0.7. So you need a minimum settling time should be less because it's being a sensitivity. So that is zero
yeah, yeah.
point 0.7. Differentiation of ramp response is a dash response. So if you differentiate a ramp response, what will it be? A, step. B, frequency. C, impulse. D, none of the above. So ramp response is your input rises with temperature with time. So it's kind of a linear. So that is a ramp response.
Yeah.
So if you differentiate that, what
Yeah,
will
with
it be?
respect to time, with respect to that means it will be impulse. It is single, no? AYT.
Yeah. So
It will be
but
C. Looks.
see if you take it as a line or y equals to mx, as in that y is your
Yeah,
output and if empty, and we'll leave the c because it starts from 0. So if you differentiate with respect to t, you get m, and that is the slope that
yeah.
will remain constant.
Then
So
stable
yeah,
ఉంటుంది, no?
so it'll
Stable means
yeah, so it'll be option A, step.
yeah. Okay, sorry.
Moving on to the next question. According to the property of impulse test signal, what is the value of an impulse at t equals 0? So we have property of impulse test signal. It's asking what will be the value of impulse time was t equals 0. A, 0. B, unity. C, infinite. D, unpredictable.
Infinite, no? T is equal 0, it will go peak.
Yeah. So impulse is the
A by
change in momentum in time. If you time it's very small, and your the momentum change is same, so that impulse will be very large, because your time you're bringing down that whole this to a very small amount of time. So that time the impulse at t tends to 0, the impulse will go to infinite. So the answer
infinite,
is
yeah.
option C. So moving next, which among the following is R and the illustration of a sinusoidal input? A, setting the temperature of an air conditioner. B, input given to an elevator. C, checking the quality of speakers of music system. D, all of the above. So it's asking what could be the sine kind of wave input. So
This is sin
this
omega t. Yeah, sin omega t. Okay. Um, all of the above is setting of temperature air conditions. No, setting
see
temperature. Yes, sir.
if you set an temperature, that it'll change, and if you can say based on operating condition you set it vary, but that it's not clearly defined. And if you see B, option B, input given to an elevator, so that is also, it's not a sine wave, so you just give one this thing and it's not. But if you want to check the quality of speaker of his music system, you have a certain sound which has to be played, and you check for that it should oscillate between some maximum minimum display, so it will go through a harmonic
Yeah.
this one. So the option will be C.
Yes.
So moving on, next question. The magnitude and phase relationship between dash input and the steady state output is called as frequency domain. So magnitude and the phase
Mm,
relationship is asked between the what type of input and the steady state output. It's basically the QIS and that relation. So you have certain that what would be give you the magnitude and phase relation.
Magnitude and phase, the 10 inverse of omega t. No? That is,
That gives you phase lag. Here, what has been asked, the relationship. You have some magnitude
relation.
and you have some phase. If you see, step has magnitude, but it doesn't have phase. So this
Sinusoidal,
yeah, the
sinusoidal.
answer will be option C.
See, yeah, present, yeah.
So moving on to next, we have, if a linear system is subjected to an input RT equals A sine omega t, what output will be generated? A C is C is the output. So B sine omega t plus phi, C B cos omega t plus phi, C B tan omega t plus phi, C B cot omega t plus phi. So you are giving an input A sine omega t.
Uh-huh.
So it's a linear system. You have R equals to A sine omega t as the input. So the output expected, if you have sine omega t, cos omega t, tan omega t, and cot omega t, and your magnitude is also changing B. So this here magnitude is B, and you're also a phase lag.
Sir, if input is sinusoidal,
Yes.
output also should be sinusoidal, no?
Yeah. Correct. So it will have a phase lag phi, but the say nature of that will remain same. It will be sine. So the sine wave remains sine, but it will be shifted by some amount due to the phase
Okay.
lag. So that is
Uh,
option A. So moving next, you have a steady state error in step input. You have a step input, and what could be the steady state error in that? You have QIS
that is,
lambda. Lambda is a time constant. QIS by lambda. QIS lambda e raised to power minus t by lambda. QIS lambda by divided by e raised to power minus t by lambda.
that is
QIS,
A answer.
yeah.
UIS time constant. Yeah.
Here
A.
its answer will be option A. QIS is the ramp response, the rate at which the input is rising. That is the QIS dot.
Yes.
And lambda is the time constant. So the steady state error will be the product of those. So option answer will be option A. So moving next, in first order system, frequency response, the phase angle is phi. The question mark is the phi. Is equal to A tan inverse minus omega lambda, B tan inverse omega lambda, tan inverse minus omega by lambda, tan inverse omega by lambda.
This answer A. A.
Yeah,
10 inverse.
correct. The answer is option A. So this is the amount with which the output will shift. So next, it's a link question. We have three questions we have passage, and we have three questions linked to that. The question is liquid thermometer. There's a liquid thermometer as its glass bulb protected by a well. So we have a assuming the old type thermometer, you have a mercury, and then outer you have a glass, right? So that kind of thermometer, it's protected by a well and a glass bulb. So the thermometer is subjected to a temperature which is changing with plus or minus 15 degrees Celsius every 100 seconds. So it's changing between plus and minus 15 from the mean value for every 100 seconds. The temperature, the measurement system may be idealized by a double capacity system with time constant of 20 seconds, and for the bulb and 40 seconds for the well. So you have to take into account two, both the glass bulb and the outer well which is covering the glass bulb. So both are acting together as a measuring instrument. So that is what is mentioned as the double capacity system. So each of its time constant is 20 and 40. And you also are again given that the amplitude is changing with 15 degrees Celsius, the temperature. So you know from there, and the period of oscillation is 100 seconds. So the questions are, what is the maximum value of temperature indicated by the thermometer? So you have 3.45, 4.45, 2.45, 5.45. Then the phase angle in radian. What is the phase angle? Then third is time lag in seconds. So please try. I'll give you some time, and we will go over the solution. The third question is time lag. You have to find out time lag, maximum value of temperature, and the phase angle. So did you get it for first one? Okay, okay, I'll give you another 2 minutes. We'll see. Go over the solution after that. We'll see. Uh, think we'll go over the solution. I'll just repeat the problem and then we'll see the solution. We have a liquid thermometer. We have to measure a temperature of some liquid or something. So it's at some temperature T, and this thermometer is made such that you have a glass bulb, and the glass bulb is covered by an outer well. So you have two systems acting in parallel, acting together. That uh, is measuring the temperature with the plus or minus 15 degrees Celsius. So it's oscillating between plus 15 and minus 15 with a time period of 100 seconds. So that's what the first line says, and you have been given the individual time constants of the bulb and the well. So the time constant for the bulb is 20 seconds, and for the well is 40 seconds. And we have been asked to find out the maximum value of the temperature the thermometer will show, and what will be the phase angle of that, the phase angle radian, and then the next is the time lag. So the solution goes like this. So we know the time period is 100 seconds. So the frequency that omega, frequency will be 1 by the time period. So omega is 2 pi by t. So it will be 2 pi by 100. So that will be the omega. So it will be 0.0628 radians per second. Then we know for it has two systems. If you see, it says one is the bulb and the other is the well, and each time constant is 20 seconds and 40 seconds. For both of this, the omega will remain same. So the individual calculation for the bulb and the well will be omega t1 and omega t2. So that will give you 0.0628 into 20. This is for the bulb, so that is 1.256, and omega into t2 for the well is 0.0628 into 40, that is 2.512. Then we have the amplitude ratio. What will be the amplitudes of the output and the input? And we know that the amplitude ratio is 1 by root over 1 plus omega tau 1 square. Tau 1 is the time constant. Tau is the time constant. So 1 plus omega tau 1 the whole square into 1 root of 1 plus omega, because it's happening in two stages, right? First, the temperature thermometer is made up of two parts. So the outer well will come in contact with the fluid, which has to be temperature has to measure. So that is the input. The temperature of the fluid is the input, and that and you have the well. So that ratio, and then the ratio of the well and the bulb. So if you multiply that, you get the ratio between the input and the output last bulb reading. So that's why you multiply this. So 1 by 1 plus omega tau 1 square the square root, and 1 plus 1 by root over 1 plus omega tau 2 the whole square. So you substitute the values here. So you get theta naught and theta I ratio is 0.23. So now we need the maximum indicator temperature. We know that the amplitude is the temperature is varying from T. Just a second. We know that the temperature is varying between plus 15 and oscillation between 15 degrees Celsius, positive and negative. And so the maximum temperature it can show is 15 into 0.23, so 3.45. So the temperature it will show is some temperature of the fluid, which is not given, which is not required actually. So it will be show that T plus 3.45. It will show 3.45 degrees Celsius more or less. So that is the oscillation of the instrument. So the actual variation is 15 degree. You get 3.45 from the measurement. So the next part of the question was to find out the angle of lag. So angle of lag is, tan inverse omega tau 1 and minus of. So that. So and if you substitute those values, and this phase lags can be has to be added, because each of it is acting. So first the fluid and the well, so it will create some phase lag, and that goes as an input to the next stage of the glass well, that will shift it next to another level. So there will be two phase lags which will get added. So that's why there's a summation. So tan inverse of omega t tau 1 we substitute there, and tan inverse 2.512. So if you substitute this, so the radiance output is 2.089. So this amount is the lag between the input and the output signal. Next, how to calculate the time lag. So what we know is time lag is 1 by omega into the what lag we have. So omega we have already calculated from the previous calculation, 2 by t is 0.0628, and we know angle of lag in radian is 2.089. So 2.089 by 0.0628 is 33.26 seconds. I hope this is clear. If you have any doubt, I can clear.
Yes, sir. Yes, sir. It is clear.
Okay. Then I'll move to the next question. Find the rise time. It's 10 power minus 6 seconds for a critically damped second order system subject to a step input where the natural frequency is 100 kilohertz. So we need to find rise time. I'll give you in 2-3 minutes to solve. This 10 power minus 6 is you need a time in microseconds. So we need rise time in microseconds. That's why it's indicated 10 power minus 6. It's not 10 minus 6, but it's 10 power minus 6 to show that we need to calculate rise time in microseconds for a critically damped system with a natural frequency of 100 kilohertz. ஹலோ ஹலோ கால் பண்ணிருந்தீங்க. சொல்லுங்கள். மாதா அரிசி என்ஃபீல்ட் ஷோரூம் ஆப்போசிட்டில் ஒரு ரோடு போவோம், மாதா அரிசி மட்டி. அதிலே வந்தீங்கன்னா டெய்லி கார்த்திகா புகழேந்தி அப்படின்னு வீடு பேர் இருக்கும். அது கொஞ்சம் தூரம் தான், ஒரு கால்வாய் இருக்கும், கால்வாய் பக்கத்துக்கு. புகழேந்தி கார்த்திகா அப்படின்னு ஆ so we'll see how to calculate this. We need to find the rise time, and this is second order system which is critically damped. Critically damped, the damping ratio is 1, and this is for a subject to a step input, and we have a natural frequency of 100 kilohertz. So the options are 6.19, 3.19, 5.19, 8.19. This is all are in microseconds. We need to find rise time in microseconds. So the answer is 6.19. So we'll see how. we know that natural frequency is 100 kilohertz. So converting this to radians, we know this f is 100 kilohertz. So you need to multiply by 2 pi into f, 2 pi into 100 kilohertz. So that will give you 6.283 to 10 power 5 radians per second. So we know that the system is critically damped. So zeta, that is C by Cc, is 1. So we also know that the average ratio is 1 minus bracket 1 plus omega natural frequency omega n into t into exponential raised to power minus omega n t. That is time constant, tau or t. And then the rise time is obtained when this ratio is 0.9, or the signal reaches 90% of it. So therefore, when you substitute 0.9, the difference between 1 and 0.9 is 0.1. So the right hand side, the last equation, the right hand side, that is equals to 0.1. So when you solve this for omega n t, what we get is omega n t is 3.8901. So from this we know we can find out the rise time for how much time it will take to rise to the 0.9 value of the input signal. So we already calculated this omega n, which is 6.2832 in 10 power 5. We substitute this in the t rise equation, and then we can find the total time it takes to rise. So it's 6.191 microseconds. See, this case we know this expression, we have to just substitute that as 0.9, we'll get all the rest of it. I think this is clear. If you have any doubt.
Further,
Yeah.
yeah, the expression we have to remember that Sir has been already this has been discussed. The critical depthing and under depthing and the equation we have to remember. 1 plus
Uh,
1 plus.
I think the I don't I can question may come, I don't know, because the examples can be similar to the assignment problems. So or else you can get this equation from the actual equation, the generalized equation, where you, if you know second order system, you can solve for the differential equation and get the equation. So that also you can do. That is
Okay.
also one way of, if you know how to solve the differential equation, that is I think a easier way of it. Or else you have to remember the equations.
This equation. Okay.
So it
Okay,
depends.
I got it.
If you remember how, if you know how to solve, you have to take that into complementary and the partial this one, and you have to solve those. And that I think that is one way of remembering it. It's you already know how the generalized expression is, so you can get it from there also.
Okay, okay, sir. Okay, sir.
Yeah.
Okay, sir.
In this case, the other part which is to be remembered is the 0.9, because the rise time we have to calculate, that we have to, it's kind of given, it's not directly given, so that is also a catch here, so you have to remember that, so you'll know. So moving on to the next question. A certain thermometer has a time constant of 15 seconds and an initial temperature of 20 degrees Celsius. So we have a thermometer which also been given the time constant 15 seconds, and the initial temperature of the thermometer is 20 degrees Celsius. It is suddenly exposed to a temperature of 100 degrees Celsius. So it's been suddenly exposed. So this is a step input. Determine the rise time, that is the time to attain 90% of the steady state value. So we have to find the rise time to reach the 90% of the steady state value. Steady state value is 100 degree, and the temperature of at this time. So what will be the temperature at that time? So if the thermometer was subjected to, so it's the next part of the question, the same thermometer. So now instead of giving a step input of 100 degrees Celsius, you are saying that if the thermometer was subjected to a very slow harmonic disturbance having a frequency of 0.01 hertz. So the frequencies you have given 0.01 hertz. In this case, the time constant is still 15 degrees, 15 seconds. So In this case, we have been asked to find out the time delay in response of the thermometer and how much does the steady state amplitude response decrease. So we have to find time delay and also the decrease in the amplitude, how much it decreases from the input. So the question is in two parts. First is you are having a step input, and the second you have an harmonic or a sinusoidal input. In the first case, you have to find out the rise time and the temperature at that time, and the second case you have to find time delay and that amplitude. I'll give you some time. You try. We'll go over the solution after that. யார் ஃபோனில் தான் வந்துச்சு, எனக்கு தான் வந்திருக்கும். இந்த வந்திருக்கு ஃபோன் நம்பர் எடுத்து எடுத்துகிட்டு போ. இல்லை ஓடிபி வர சொல்லி இல்லை வரும்ல, ரொம்ப தள்ளி போயிடாது, எனக்கு சிக்னல் வராது, உன் ஃபோனும் வச்சுட்டு. I think the first part is fairly simple. You just a first order of a system and a step input. I think we know that amplitude ratio is e raised to minus t by tau, time constant, time required by tau. You have to just substitute that 90 percent and you have to get the time. And you have to substitute the time and then find out the temperature. So that's a fairly easy problem. If you have solved, may I know the values? Yeah, I'll give you we'll see the solution in 2 minutes. Give you an additional 2 minutes to solve. So we'll see the solution. I'll go over the question. We are having two parts of the question. One having a step input, and next we have a uh, yes. We have any query?
Yes, sir. Please go, sir.
Okay. So the question is in two parts. We have one step input, one harmonically excited input, and both the time constant is 15 seconds. And for first case, we need time and temperature at 90% when it reaches steady state value. And second, we need to find time delay and the amplitude. So the first is, we know that the temperature, initial temperature is 20 degrees Celsius, and the final temperature, the steady state value it could reach at when the temperature when the time is kept at a very large, or we can say T is tending to infinity. So in that case, the temperature will reach the steady state value. So that is the 100 degrees Celsius, which is the fluid temperature initially given. And then we also know the time constant, which is 15 seconds. So when it for it to reach 90% of the rise time, so when it reaches 90% of the time, means the difference between the temperature of the fluid and the thermometer will be its 10%. So that is 0.1. When it reaches 90, so the difference will be 10%. So that's the idea. So it will be 0.1, which will be equals to e raised to power minus time by the time constant. We know the time constant. We substitute the time constant, and we can find out the time requires to reach that value. So in this case, it will take 34.54 seconds. And then to find out what the temperature will be, we know that the error is still, we need to find what will the temperature at 90% of that. So we know that it will be 0.1. We substitute the rest of it, the difference in it at then the time, then divided by the maximum difference, or the time difference at t equals 0. So we can say the time which we have to find minus the fluid temperature, divide by 20 is the initial temperature of the thermometer, minus the fluid temperature, so equals 0.1. So when you solve this equation, we get the time at t equals 34.54 seconds, which is 92 degrees Celsius. Or the other easier way you can see is, we know that it has already reached 90%. So yeah, the max difference is 80%. So that's 8%, 8 degrees, the 10%. So 100 minus 8, 92. So this is moving on to the next part. This is harmonically excited. So we know omega, they have given frequency as 0.01 hertz. So the omega is 0.06283, which is 2 pi f. F is 0.01 hertz, and then this gives you in radians per second. Then the time constant is still same, which is 15 seconds. So the omega t, or the omega tau, equals 0.06283 into 15. That will give you 0.9425. So now we have been asked to find out phase lag. So phase lag, we know phase lag is minus tan inverse omega tau. So that will give you, when you substitute 0.9425, the tan inverse of that is minus 43.3 degrees, or in radians it's 0.756. Then we have been also been asked to find out we have been asked to find out time delay. So we have found out phase lag. Time delay is phase lag divided by omega. So phase lag is 0.756, and then omega is 0.06283. So we substitute that, and then we'll get 12.03 seconds. Then the amplitude response decreases according to, so we know the amplitude ratio, which is equals to 1 by root over 1 plus omega tau square. So which will be equals to 1 by root over 1 plus omega tau, we have already calculated 0.9425. So the square of that, which will give you 0.7277. So the ratio of that amplitude will be 0.72 times the input amplitude. So that we have what has been asked. So I hope this is clear. If you have any doubt.
Yes, sir. You can go ahead.
Then moving on to the next question, we have a first order system which experiences a phase shift of minus 45 degrees at a certain frequency omega 1. So we have given the input signal is omega 1, and because that the first order system experiences phase shift, that phase shift or phase lag of 40 minus 45 degrees. By what fraction has the amplitude decreased from a frequency of 1/2 this value? So the next question is, because of omega 1 there is phase lag of minus 45 degrees. So what is the amplitude decrease when the frequency is halved? So now the frequency is omega 1 by 2. So at this case, what will be the amplitude decrease? So I'll give you 2-3 minutes. Please try. Okay, we'll see the solution for this. We know it's a first order system, and we know that phase shift is 45 degrees for phase frequency omega 1. We need to find the amplitude decrease. So we'll see. So phase lag is given as minus 45. So from this we can find omega t, omega tau. So we already know that phase lag is minus tan inverse omega tau. So phase lag is already given. So we will take tan of 45 minus 45. Minus will get cancelled off. So tan of 45 is omega 1 tau. So which will be tan 45 is 1. So omega 1 tau is 1. So the amplitude factor is for this case will be 1 by root over 1 plus omega tau square. So we know omega tau is 1 because of 45 degree phase lag. So we substitute that and we get 1 by root 2. So 1 by root 2 is 0.707. So this is the amplitude ratio for the first case when the omega is given and for which the phase lag is 45 degrees. So the next part of the question was, what is the amplitude decrease when the omega frequency is halved? So when the omega frequency is halved, the omega tau will also get divided by 2. So that will also get halved. So that will be omega tau is 0.5. Here this being there is no change in the system, just the frequency of the input signal is getting changed. So the tau remains same. So we know omega tau is 0.5. So So the amplitude ratio again is 1 by root over 1 plus omega tau square. So we put omega tau is 0.5. So now in this case we'll get 0.894. So if you check how much difference is this, is there is a 7.91% increase. Sorry. If the frequency of reduces by half, so in this case there is a increase of 7.91% in the amplitude. So that's what we can infer from this question. I hope this is clear.
Yeah, okay, sir. Right.
Okay. So we'll move to next question. I have a second order system which is subjected to input below 75 hertz. So the second order system, the input is below 75 hertz, and it is to operate with an amplitude response of plus or minus 10%. So amplitude response, what it should be, we have to design a system such that for this frequency of the input below 75 hertz, we need an amplitude response which is plus or minus 10%. So that is what the goal is. So how will we go through this? So the input, the required input is there. We need the omega is 75 hertz, frequency is given, and then the amplitude ratio which is also been given. So basically we need to find out the time constant. So that's the other parameter which has to be known for the system. I'll give you an 2-3 minutes to solve. Sorry, I made a mistake. We have to find out the natural frequency of the system. We'll go over the solution. So in this case, the amplitude ratio, assuming this similar to a spring mass system, so that x not k by f must remain between 0.9 and 1.10. So we know that the amplitude ratio should lie between plus or minus 10%. So that's what we have been asked. So this being a second order system, we need to find out the damping ratio. So that's what actually we know omega, and we need to find out omega n. So as this is a open-ended problem, because it can be anything. Because we don't know the damping ratio. We are what could be the actual. We go with assuming this is amplitude of 0.7. We are moving forward, but that could be anything. So for this case, we'll see how to solve this. So because damping ratio should lie between 0.6 and 0.8, we are taking 0.7. So from for that case, and then to assume to see the rise value of 0.9, which is the error, the amplitude ratio, which is plus or minus 10%. We see the lower limit 0.9. We substitute that. So for this case, we solve for omega n. Here we know the amplitude ratio is 1 by root over 1 plus zeta square omega by omega n, the damping ratio, omega zeta square plus 2 uh, sorry c by cc is zeta, omega by omega n square plus 2 zeta omega by omega n the whole square. That is the amplitude ratio for the second order system. So here we didn't know omega n and the c by cc, which is the damping ratio. So now we have assumed damping ratio is 0.707. We substitute that, and then we find omega n. So for 0.9, which is the amplitude ratio, so we find out omega by omega n ratio values here, so which will give you 0.696. So we know that for the system is below 75 hertz. So for 75 hertz, omega is 471 radians per second. So the minimum value of omega n is, we substitute for 471 radians, we'll get 677 radians per second. So the actual frequency of the system should be 677 radians per second. Is this clear, or should I repeat?
Yes, sir. Yes, sir. It's clear.
Okay. So I'll move on to the next question. We have first order system, which is subjected to a harmonic input of 3 hertz. The system has a time constant of 0.5 seconds. We need to calculate the error of the amplitude response and the phase lag. I think it's a easy problem. We know we have given the frequency and then the time constant. So I'll go over the solution. We'll see. You know omega is 3 hertz. So for it to convert to radians 2 pi f, it will be 18.85 radians per second. You also know the time constant is 0.5 seconds. So the phase lag is minus tan inverse omega tau. We substitute omega tau values, omega 18.85 and tau 0.5 seconds, which we get minus 8.39 degrees. And then we also know that the amplitude ratio is 1 by root over 1 plus omega tau square. So there we substitute omega tau values, 18.85 into t, the square of that plus 1 square root. So you will get 0.1055. So that's what was asked in the question. We have to calculate the phase lag and the amplitude response error. So the error is the difference. So we have found out both.
Sir, dynamic error, this one minus one. One
Sorry,
problem given that.
sorry, dynamic error.
Dynamic error is equal to 1 by root over of omega square square plus 1 minus 1. No? Minus 1. The last one problem
Yeah,
was the
see,
spin mass system.
you are saying about this one. X by x 1 minus root 1 plus omega 1 t. Is this the one you are talking about?
Yeah.
See, this is a second order system, and there is a damping
Uh-huh.
because of that. That is a simple first order system.
Okay.
So the first order system, the amplitude ratio is 1 by root over 1 plus omega tau square.
Okay, sir. Okay.
There will be no minus 1 here. I hope this is clear.
Okay, sir. Okay, sir.
Then if we move on to the next question, we have a temperature sensor is to be selected to measure temperature within a reaction vessel. So we have a reaction vessel, and then it is suspected that the temperature will behave as a simple periodic waveform with a frequency somewhere between 1 and 5 hertz. And then the sensors of several sizes are available, each with known time constant. So based on time constant, select a suitable sensor, assuming that the dynamic error is plus or minus 2% is acceptable. So in this case, we've been asked to find out time constant, or to select a better sensor to find out the temperature. So we have given the frequency and the error also. So you have to find out a suitable sensor for this case. See, in this case, this is the first order system, and it's also sinusoidal input. You can say this says periodic waveform. We can assume a sinusoidal. We can assume cos or something else also. Then we have already tried with sinusoidal. We will go ahead with sinusoidal, and we know that frequency is given, and we need to find time constant, and we have been also given the error, which is plus or minus 2%. I'll give you 2 minutes to solve and think over the problem. We'll see the solution. I'll repeat the question. We need to find we have a reaction vessel, and we have to measure the temperature within the reaction vessel. And we need to use a sensor, temperature sensor, and we have multiple temperature sensors, and we know that it behaves in a periodic waveform. And so it's a frequency response system, and then we have frequency of lies between 1 and 5 hertz, and they say we are able to choose sensor based on its time constant, such that the dynamic error will not uh, go above plus or minus 2%. So we'll see how we'll go about this problem. So we know that frequency lies between 1 and 5 hertz, so that is given, and we also know that the dynamic error should be less than or uh, uh, equals to 2%. So 2% is 2 by 100, 0.02, the ratio of the input. So, and then we also know that it behaves periodically, so we are assuming that f of t is a sin omega t, and since the error should be less than less than or equal to 0.02, we would set a magnitude ratio or the amplitude ratio to lie between 0.98 and 1.02. So that's where it should lie between. And since this is a first order system, so first order system, it will not overshoot. So that's why the maximum it can reach is amplitude ratio equals to 1 or less than that. So it will not go overshoot. The overshooting happens in the second order system. So that's why it cannot go above 1.1. So 1.02 we neglect that. So it will be lie between 0.98 and 1. So the amplitude ratio will lie between 0.98 and 1 because of the there is no overshoot in first order system. And we also know that the amplitude ratio in first order system is 1 by root over 1 plus omega tau square. And from here we know that amplitude ratio should lie between this 0.98 and 1. So this omega t should also lie between a region. So for first case we will take omega the amplitude ratio as 1. So for that omega tau will become 0. So if you put omega tau equals to 0, this will become 1. The whole amplitude ratio will become 1. So it should lie between 0, and if you take the amplitude ratio as 0.98, from this the amplitude ratio equation will get omega tau equals to 0.2. So for the amplitude ratio to lie between 0.98 and 1, it should lie between 0 and 0.2. If you see for higher amplitude ratio, the omega t will go to a lower value. And then we have founded omega tau, and then we need to choose the sensor based on its time constant. So we have omega and tau, but the problem is here is the frequency lies in a region, so 1 to 5 hertz, and we need to find tau. So for a fixed time constant, the smallest value this will occur at largest frequency. So you substitute omega equals 5 hertz. Then for that, if you 5 hertz will for 0.98 amplitude ratio, will get tau as 6.4 milliseconds. So omega tau is 0.2 for 0.98, and we substitute omega value. From there we will find out that tau is 6.4 milliseconds. So we have to choose a sensor such that time constant of that is 6.4 milliseconds or less. So we have to choose from the available sensors, we have to choose such that the sensor having a time constant 6.4 or less than that, we can use that for measuring the temperature in the reactor vessel. So I hope this is clear. If you have any doubts, I can go over.
Okay, no doubt.
Yes. No. Okay. So it's another next problem. We have a temperature probe, and which has a time constant of 10 seconds. So when it is used to measure a temperature in a particular gas flow. So the gas temperature varies harmonically between 75 degrees Fahrenheit and 30 degree Fahrenheit. And the period of oscillation is also given as 20 seconds. So it's 20 seconds period, or the frequency you see, it's 0.05 hertz. So it's 1 by 20. So what is the temperature readout in terms of the input gas temperature? And then the next question is, what time constant should the probe have to give 99% of the correct temperature amplitude? So we need to find two, the temperature amplitude, this amplitude, and the time constant. So this is also a first order system with a sinusoidal or periodic input. So if we see how to solve, we'll see how to solve this problem. So in this case, we know that the temperature is oscillating between 75 and 30. So we can write the equation of that gas which is varying as 300 plus 75 by 2, which gives the mean temperature. So that is the mean temperature, and the maximum amplitude can be the difference between the two, minimum and the maximum temperature oscillation, divided by 2, because it will oscillate between the mean. So 300 minus 75 divided by 2, so that will give you the amplitude of the wave form, or the wave signal, into, we also know that it's oscillating at a frequency of 0.05 or 20 seconds. So omega into omega t, so omega is 2 pi by t, so 2 pi by 20 into t. So that gives the temperature of the gas, how it's varying. So simplifying it, we get T, the temperature of the gases at any time t is 187 plus 112 sine 2 pi t by 20. So that's the gas temperature, how it's behaving. Since this is a first order system, we know the temperature amplitude ratio is, so amplitude of output by input is 1 by root over 1 plus omega tau square, which equals, we know that omega is 2 pi by t, and the this thing, time constant is 10 seconds as given in the problem. We substitute that, so we get uh, 1 by 3.3, and the amplitude which maximum is 112. Since this is a dynamic error, we need that ratio, so we use 112 divided by 3.3, will give you 34 degree Fahrenheit. So we have found out the temperature which has been given. What is the temperature readout in terms of input gas temperature with respect to the input gas temperature? So in terms of so this is 34 degree Fahrenheit plus mean 187 plus 34, that will be the temperature shown. And for the next question was, what time constant should the probe have to give 99% of the correct temperature? The phase lag for a pulsing period of t equal 20 seconds is phi is minus tan inverse omega tau. So for this case, we'll get 72.5 degrees. So time lag will be 72.5 divided by 360, which will give you 4 seconds. So we have found out the temperature and then the time lag for the first question, and then now moving on, we have to find out for 99% amplification ratio, what is the time constant. So we know the amplification ratio, or the can say output input, the magnitude ratio or amplification ratio. This one for a first order system is 1 by root over 1 plus omega tau square. So we have been given that it's the amplification ratio is amplitude ratio is 99%, so which is 0.99, and we also know omega is 2 pi by 20, so we substitute that, and the only unknown is tau. So we can get from this equation, which will give you the tau is 0.45 seconds. I hope this problem is clear. If you have any doubts, I can clear. Yes.
Yes, sir. It is clear, sir.
Okay.
Okay.
So that's all the problems I prepared for today. If you have any doubts or queries on this week, fourth week, we can discuss.
Fourth week, the assignment has been submitted.
Uh,
and this is fifth week is going on. Yeah.
Okay. If you have any queries, please.
So this slide has been shared. Okay? Slide
Slide.
what you prefer.
Yeah, I think I don't know how this goes on, but I they will be conveying some uh, the
Yeah, last first of this. Yeah.
YouTube and slides. I think we give it. I don't know how what they will pass it on to the enrollees. So I think hope the YouTube links is available. I don't know about the file, but the YouTube link I think will be available. So you can see in that
Yeah,
YouTube.
first side, first week and second week this presentation is available.
Okay, okay. Then
Third week is still, third
I
week it is not still it will not
okay.
come.
I think that
The,
there's some issue in uploading. I'll upload. I'll re-upload. I'll upload that and this
okay,
week's slides.
okay, okay, sir.
Okay. Any other queries, or else you can close the session.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Yeah. Thank you.
Thank you.